Hey everyone, welcome to another YouTube video on another paper review. And today I want to talk about this paper, a simple framework for contrastive learning of visual representations, or it's more popularly known as SimCLR, version V1. So it's a paper by Ting-Shen et al., a paper from Jeffrey Hinton's lab. So let's just dive right into not the paper, but first I want to talk about the idea of self-supervised learning. As we all know, typical supervised learning ideas, classification, and even in the field of reinforcement learning, there are issues. And these issues include you need large amounts of labels / rewards, and you're unable to learn on multiple tasks. And typically these models do really well on interpolation problems, but their extrapolation results are very poor and do not work on new scenarios. So the hope is that self-supervised learning can be used as promising methods to build models with common sense. Or as Jan LeCun calls it, the dark matter of intelligence. So what the intuition is that we as humans, we do not obviously just look at labels, learn a particular task, or get reward, or simply even just get rewards from your environment and work with that. We actually we build models that are general models of our environment, and we hypothesize, we try to learn about those general models, poke the extremes and see if they are correct or make changes to it. So for example, we observe the world, we learn the physics of the world, and then apply it to different scenarios, and we make our model stronger by applying those actions on the world and enforcing our model. So there is no intrinsic reward in the scenario, or there are no supervised labels. So the idea is that we can use some sort of self-supervision to learn a general theory of the world with no objectives. And this is already used in, I would say, in language models. So it's very common in language models. So if you look at masking or in transformers, in BERT, etc., the idea is that you are learning in a self-supervised manner to predict what will be the word in the mask location. So, but in computer vision more recently, the idea is that you do not need a large amount of labels. You can create these task agnostic settings, meaning you do not have like a particular task or a reward generating. You do not have like labeled supervised tasks. So you just create these simplistic tasks, I would say, simplistic ideas. The idea is that you want to predict if a particular image is, you pass it to a rotation function, it rotates it by say 0 degrees, 90, 180, 270. Now, can you pass it through a convolution neural network model to predict by how much angle it was rotated? Or you crop particular sections from an image, and you want to be able to predict which part that particular cropping came from the image. And these are, by learning these tasks, you are essentially building models that are more generalizable or more learn better representations. So, which is the main goal. You want to learn good representations, and you do not want human intervention or supervision, because getting those labels are very hard. So you learn on these, you use a large amount of unlabeled data, train on these tasks that are simplistic, and then the idea is you collect labels for a small subset of images for the actual task you want to perform, and then you fine-tune your trained model on that subset, and there is some gains because your model has already learned really good representations. So this is sort of the idea in self-supervised learning. And more recently, the notion has become that just doing learning multiple tasks by just doing perhaps a classification of where it came from, or even trying to predict sort of like a generative models are not that effective. intuition has more become, you can combine self-supervised learning with contrastive learning. In this particular paper, that's exactly what they do. They train self-supervised learning using contrastive learning models. And the idea here is shown in this figure. Essentially, you take a image of, say, a dog, a cat, etc., and you take a particular augmentation. So let T be the set of all augmentations, and by augmentation, examples are croppings, or you can say color distortions. So you change the color of the image by a particular value, you make it grayscale, that's another augmentation, you flip it left, right, vertical, etc., rotate it, those are all augmentations. So for example, so you take two augmentations, so T and T dash, and you pass the image to both the augmentations. So you get two versions of the same image, xi and xj. And now you pass it through your convolution neural network, which is f, the function f, and you get two representations, hi and hj. Now, you could either, the idea is that you want to learn in a contrastive setup. So you want to make sure that the representations of hi and hj, but in this particular case, they actually use a projection head network. We will go into details as to why that's useful later on. But the idea is you take hi and hj to another projection network, which is simply a fully connected neural network to zi and zj. But what's more important is that in a contrastive learning setup, you want the representation between these two images, the final representation, zi and zj, to be equivalent because they are the same image. So you want to maximize the agreement between zi and zj. And if you learn by this strategy, you get a really good representation of the images. You become agnostic to certain like disturbances in your entire data set. And now if you collect, fine-tune this model on like a very small subset of label data, this model performs really well. So in this particular paper, these are the different augmentations that are used. So crop and resizing, crop, resize, and flipping, color distortion, color jittering. So color distortion drop is you just drop the color. Jitters, you change the color by set values randomly. You rotate them 90, 180, 270. Cutouts, so you cut out a particular section of the image, add Gaussian noises, add like blurs, and finally Sobel filtering. So these are different augmentations used, and the idea is that hopefully these augmentations represent the different sort of invariances that you want to build into your model. So you want to be invariant, you want your convolution neural network to be invariant to croppings, different resizes like scales. You want it to be invariant to colors, invariant to, so either black and white or jitters. You want it to be rotational invariant. You want it to be able to make predictions, even though some part of it are not visible. So cutouts, if there is noise in your images, you want it to be invariant to that. And you want to be invariant to Sobel filtering is interesting, but I'm not sure why you want to be invariant to that. But I guess you also want to be invariant to that. And to be invariant to all of this, you need to learn really good representations that capture all of these invariances. So by training this model in the contrastive learning setups, you're gonna be invariant to all of these different augmentations. And that's the idea. So just jumping into the algorithm used in the paper. Idea is the very simplistic algorithm. The idea is that you sample a mini batch during training. So let's say the mini batch size is n, and for all n, what you want to do is you draw at this stage two functions. So let's say it's flipping and rotation, and you take these two functions. You pass all the images through these two functions. So T is say flip and T dash is say rotate by 90 degrees. So you pass the image at K. So you pass that particular image through flip. pass that flipped image through the convolution neural network, pass that output of the representation of the convolution neural network into the projection head network, and get the final representation Z for that particular flipping function. Now you do the same thing for the rotation function by 90 degrees, and you get Z2. So you get two Zs, Z2k minus 1 and Z2k. Now what do you want to do? So here you want to maximize the similarity between those representations. They should be almost equivalent because they are the same image. So the idea is that you find the cosine similarity between those two representation vectors for the images. And now, if you think about it, those particular images, so those two images are for that particular image in the batch. Now your entire mini batch can actually be used to train the model in a way that, for example, you can use it in a triplet way, mining way. So if you think about contrastive learning in a triplet style, all the rest of the mini batch except that image is going to be negative examples for those mini batches. Now now you could do that, or you can actually just think about those as examples that are of different classes. And if you do that, then you can simply use your cross entropy loss, the most familiar cross entropy loss, where you want to maximize the cross entropy loss for you want to maximize it for the images, the two images that have been augmented for that particular image, and you want to make sure that they are minimized across all the rest of the images. So essentially, you want to make sure your cross entropy loss is low, and that's exactly what you do. And this T function here, the tau function, is essentially the temperature by which you want to control the cross entropy loss. I'm not going to go into detail into that, but you just want to maximize the agreement or the similarity vector between the two augmentations for that particular image and minimize it for all the other images. And this variant of this loss is called, I think, the XT entropy loss. So actually, I may pull up the paper later so we can go through that there. And at the end of the training, after all batches have been completed, all epochs have been completed, all you need to do is keep the encoder the convolution neural network F dot, and throw away the projection head, and then fine tune F dot for the task that you want to learn on, and you're good to go. It's a very simplistic idea, but there are so many details in this paper that I think is more useful to learn about. That's not captured when you just go through the algorithm. And I'm going to go through those details, those takeaways. Here, some of them here, some of them actually I might dive into the paper at the end of this presentation. So the first thing that the most important thing is actually that batch size matters a lot. So the bigger the batch, the better your performance. And they use batch sizes of almost 8,192. And the reason, it's obvious that why batch size would actually help in this particular case compared to, if you look at traditional supervised classification or recent works in that, the law 3 hypothesis, etc. The batch size is usually very small. It's like 32, or even recommendations of smaller batches is like 16. This is so that there's you do not fall into very like a local minima, and having smaller batch sizes helps noise. By adding that noise, you are able to escape those local minimas and go into a bigger minima. I would say a global minima. But in this particular case, here, it's also important to note that the rest of the batch, except the particular image, is actually used as negative examples during training. So if you think about it, there's a for loop for the batch. There's a second for loop for going through the rest of the examples. So compared to this, but compared to, let's say, image 100, you go through all the rest of the images that you've collected in your batch as negative examples during training. And so those are all gradients that is being collected across the batch. So that would effectively create a lot of great like training examples, which would be really useful. So that's one of the intuitions there. Additionally, you also see that large training epochs, like the larger the training epochs, the less important the batch size becomes. So you can see that there's accuracy increases the more the training epoch is. So at high training epochs, the importance of batch size actually reduces. So that's another result. Oh, and yeah, to train these ridiculously large batch sizes, they use around 128 TPUs, V3 TPUs, which is a lot of compute. And yeah, we can step into that too in discussion of how reasonable it is to expect these large batch sizes for training in like a typical setting. But yeah. The second takeaway is that larger model sizes are better. So you can see the more compute you throw in and the more parameters you throw in, the better they are. So different ResNet versions. And here, for example, ResNet 4x is 4 times the width in each of ResNet 50's layers. So it's like a really large network. You can see that the accuracy increases, and that's interesting, pretty interesting. And so green is actually supervised learning, and red, if I remember, is their self-supervised learning strategy. So supervised learning on, and this is all on ImageNet, the gold standard ImageNet dataset. So you can see that red is lower than supervised learning, but it's pretty competitive for this particular ResNet. And they also did a comparative study of which transformations are actually, which augmentations are useful. So if you just do 2 augmentations or actually just 1 augmentation, which pair of them actually is useful, or which in general, you can see the cropping helps a lot in terms of so these are all accuracies on ImageNet data set. It's top 1 accuracy. So you can see the cropping gives you 39.2 accuracy. Everything else, cutouts, color, it's all like this is average accuracy. So overall cropping seems to be most effective. Interestingly, cropping with color distortion is apparently helps a lot. And this is actually more intuitive in this figure that they give. So these are 2 images, and these are 2 cropped images from 2 croppings from 2 different images. So what's important to understand is, let's say you take the overall pixel intensities for those croppings. So the crops are 4, like let's say you take top left, top right, bottom left, and bottom right, and look at the pixel intensities, average pixel intensity of a particular image, and this is the average pixel intensities of that another image. What do you see? That there's a simple way of just learning which image is which by just looking at the pixel intensities. So the reasoning here is, if you just do cropping, there is a simpler way of understanding which cropping or which image that particular cropping belongs to. That is by just looking at the pixel intensities of that cropped section. It is more clear, it's more useful to have croppings with color distortions which is the reason why there's a huge accuracy bump if you do cropping and color. That was pretty interesting takeaway from the paper. Oh yeah, and here is reasoning as to why they use the projection head, the G function. And so the intuition that the author gives is that the representation that if you were to do the contrastive learning using just H, you would need to be able to use you would need to maximize the agreement between two representations. And to maximize this, it's necessary that the model, that particular representation, should discard certain useful information such as colors, or such as it's actually not useful to learn because you want to be agnostic to changes in, say, color or changes in, say, rotation, etc. All the transformations, you want to be agnostic to it. It's actually easier to learn a representation which has no information encoding of them. So if you had to use just hedge to learn it, you're going to get a representation that is not useful for further fine-tuning. And this is what they actually show here. So if you were to use the output of G of H to simply learn a function to say whether the image has been, how much the image was rotated by, or whether it's the original image or a corrupted image, or original image versus color versus grayscale, or original image is Sobel filtered. If you were to use G of H's output, since those information are thrown away, the performances is not that great. But the intuition that the author provides is that if you use H for fine-tuning, those performances are way higher. And the reason is that you still have those information encoded in output of H. So if you were to not use G of H and use H for maximizing your representations, like the contrastive learning loss at H itself, then your accuracies will be dropping to this value instead of it being at here. So that's sort of the explanation given in the paper. And so these are the takeaways I had in the slide, but we can go into the paper if we want to. Yeah, one thing that could pop up. Yeah, one thing that's also interesting to note is that they use global batch norms. By global batch norms, so batch norm and ResNets are typically across each and every, typically over a particular device. So, so in this paper, they talk about how if you were to run across 128 TPUs, a model can actually use sort of a local information leakage to improve accuracy. And this is actually just ridiculous to even think about it. I would never think about that as a problem. But apparently models can utilize local information leakage to simply achieve particular accuracy because you do batch norm aggregation over that local device. So it's just crazy to think about the details into which the authors have went into thinking before running these experiments over these large TPUs, large amounts of TPUs. Any other interesting to... Oh yeah, I was telling you that the loss function could be anything, like it could be the NT or the temperature cross entropy loss that they use in this paper, or it could be something like a margin loss, the triplet loss that I was talking about. So they did an experiment looking at which loss works better, and apparently the temperature cross entropy loss performs really well. And finally, oh yeah, we didn't touch about the results itself on ImageNet. So if you train if you fine tune your model using just a linear classifier, so you fine tune the model using just a linear classifier, you achieves 76% accuracy on top 1 classification, which is pretty amazing. And top 5, you get 93% accuracy. And more interestingly, if you were to only give 1% of labels, so only 1% of label data to train the model after fine-tune the model, you already get 85% accuracy on top 5, and which is again amazing. It should be noted that I'm not sure if they give performance accuracies once you fine-tune with not a linear model, but with a more complicated non-linear model. I'm not sure what if it's not linears, I'm not sure what the results are. It must be noted that ImageNet, if you look at the benchmark, the current top 1 accuracy is 90.45. Well, this paper came in 2020, but still linear accuracy of 75%. It's nowhere near the current top accuracies with supervised learning strategies. So there's still a long way to go in supervised learning, but this paper was followed up with version 2, which I would be covering in the next video, hopefully. And I think I'll stop here. Let me know if you have any feedbacks. Thank you.